Welcome to 33rd lecture on electrical machines 1, and we will be discussing first another very popular test which is called sumpner test. Sumpner's test, which is also called sometimes back to back test. Okay. And as I was telling, if you carry out the open circuit test, only core loss will be there, and if you carry out short circuit test, only copper loss will be there. Both the losses will be there when the transformer will be put to operations at rated condition at that time. So neither the open circuit test, during the open circuit test, nor during the short circuit test, the temperature rise of the machine will not be the actual temperature rise when the transformer will be in operation. So what is the solution? Solution is, okay, in the laboratory, then try to load the transformer in the laboratory, connect the load and apply rated voltage at rated frequency, and connect a load such that rated current also flows, and so on. Then temperature rise can be measured, but unfortunately for a large transformers, for example, a transformers of ratings of 200 kVA, 500 kVA, distribution transformer or more I mean ratings, then such a load will not be available in the lab. And not only that, during open circuit test, from the source you are drawing only the core loss power which is responsible for core loss only. During short circuit test, burden on the supply you are putting is only of what amount of power? Very little power, which will be corresponding to short circuit test. But if you put to actual loading of a large transformer in the lab, that huge amount of power is to be drawn from the supply. This must be understood. So, during testing, always try to draw less power from the supply, at the same time see that whatever is your objective of the test, that is performed. What is the difference if the temperature rise is different? Because in open circuit test only very low temperature rise and so on. See, because of temperature rise, temperature difference, the resistance of the windings or the resistance which are representing losses, their values will change. Suppose during short circuit test you calculate R 1, R E 1, equivalent resistance referred to primary, but when the transformer is put to use, that should be corrected because of temperature rise. There is temperature rise coefficient, R t is equal to R 0 into 1 plus alpha t, etcetera. Anyway, to have a better idea of the temperature rise of a transformer, one test which is called back to back test or sumpner test is carried out. It was suggested by most probably Sumpner, and it is very interesting test. Not only the test is interesting, but at the same time, since you are studying transformer for the first time, it will also enhance your understanding whatever we have discussed earlier. That is why I have chosen this topic to be included here. In this test, what is done? Do not use actual loading, no, never. he never uses actual loading, but at the same time creates such a situation that transformer will feel that it is fully loaded. That is, rated voltage applied, rated flux will be there, and also windings will carry rated current. Okay. But without drawing very large power from the source, only it will draw the powers corresponding to copper loss and corresponding to core loss. That is the beauty of the test. Sometimes it is called phantom loading type thing. Okay. Now, let us see what this test means. Only condition for this test to be successful is that you have to take two similar transformers, not with a single transformer you can do that. Okay. Two transformers, because transformers are manufactured in large numbers. So, after manufacturing you test them, take two at a time and test them. Although you can do individual open circuit, short circuit test, that is there, but to carry out the test you require two identical rated. Identical is a very term, we do not know identical, very similar rated transformer. For example, I will take two transformers whose I will use of course small rating, say 10 kVA, just to give you a feel of what is going on. 10 kVA, two numbers of 10 kVA, 200 volt, 100 volt, 50 hertz single phase transformer, suppose you take. And then first thing what you have to do is that you have to carry out the polarity test. I will also take opportunity to explain to you how to ascertain polarity test, because that is essential to carry out the test. Unless you do not know the polarity, it will be not possible to carry out the test. It cannot be left to chances. Now, what do I mean by polarity? We told you very simple, that suppose you have a transformer whose rating is 200 volt and 100 volt. Okay. Now, what you do here is you apply, because the dot convention is not known. Dot convention, that is, if I put a dot here, what to put dot there, I know what it means theoretically, and also I can ascertain that without doing any test, provided you know the sense of the winding. But in general, for a practical transformers, only two terminals will come out from the primary, two terminals comes out from the secondary, and windings really you cannot see, is not, it will be inside a sort of black box, I mean steel box, everything will be there. Two terminals only come out here, two terminals will come out there. That is the problem. But as I told you, dots must be known. In fact, for three phase transformer connection, that is also essential to know. In case of open circuit test, short circuit test, you do not bother, it is not necessary, as you will understand now. For this particular test, why it is necessary. Now, as I told you, in this case, if what you do, you apply rated voltage. See how to find out dots. So, what you do is this, you apply, say to this winding 200 volt you apply, okay, and there is no dot markings here. Now, but you are free to choose one dot terminals of any of these windings. For example, you say that this is this side you take a chalk and mark, okay, this is my dot terminal of this winding, but that is what you cannot do now here. If this is positive at any one time, which terminal is positive on the other side, that is the goal. Okay. Now, this diagram, what you do is this, then you short these two terminals, you take a piece of wire, connect these two terminals and take a voltmeter, connect it here. That is what you do. Now, the moment you apply 200 volt here, no matter whether you have connected this or not, by transformer principle 100 volt will appear here. And this 100 volt, I am not sure whether this is dot or this is dot. The thing is, suppose let us assume this is dot, suppose this is also dot. These two coils are connected in series, as you can see, and I am measuring the voltage. What will be the voltmeter reading? 100 volt, because they are in this is plus 100 volt. What could be the other possible reading? It could be like this, dot may be here also, I am not sure. If that is the case, then what will be the voltmeter reading? 300 volt. So, it is this voltmeter reading which will help me to put dot correctly either here or there, depending upon the looking at the voltmeter reading. If this reads the difference of these two voltage, then I will put dot there. If it voltmeter reading gives sum of these two voltage, I will put dot here. Very simple logic, nothing like that. Only one thing is this about this test, the comment is, suppose the ratio of the transformer is very large. For example, you have a transformer whose rating is say 1000 volt stroke 100 volt, suppose you have a transformer. In this case, then what will happen is this. So, if you apply 1000 volt here, you will certainly get 100 volt, no doubt, and you are free to choose one dot terminals of one of the coils. So, I will suppose choose here, and what I told, I will connect these 2 points here, and I will connect a voltmeter there. In this case, the voltmeter readings will be either 1100 or 900, one of them will come. But you see, with a practical voltmeter, these two voltages are close by. So, a slight misinterpretation or somewhat wrong reading of the voltmeter you really cannot ascertain. That is the problem. If the ratios of the voltages are high, then difference and addition become of the same order. Therefore, it will be very difficult to distinguish these two readings confidently. Okay. So, in such cases, when the voltage ratios are high, it looks like this method is not reliable. So, what people do is this, in this case for very large voltage ratios, another simple test can be done, and that is called the DC kick test. DC kick test, very simple test. What is done? You do not require also large supply, rated voltage, those things may not be required. What do? You connect a switch here, much simpler than this. you switch here and take a DC source, battery say, and here you connect a zero centered moving coil voltmeter, MC voltmeter. That is all. And the positive of the battery, wherever you are connecting, put the dot there. One you are free to choose. Now, and it is also a voltmeter connected between these 2 points. Now, you close the switch. The moment you close the switch, it is not AC supply, but there will be a sudden change in flux. Therefore, we expect there will be instantaneously there will be an induced voltage. And if this is dot, happens to be dot, and see moving coil meters has got plus minus marking, is not? Moving coil meters has got plus minus marking. If current enters, it gives positive. So, zero centered meter you take, zero centered meter. So, you close this switch, there will be a deflection in the moving coil voltmeter, a short duration, steady state will soon be reached. If it gives positive deflection, you are sure this is also dot. If it gives negative, if this is dot, this is dot. So, anyway, this is called DC kick test. You select this voltmeter reading such that steady state current does not exceed the rated current of this meter, these things, but very interesting test. So, anyway, this test by doing this simple test we can find out the polarity of a transformer. Okay. So, you do this. Now, coming back to sumpner test. So, two numbers of similarly rated transformer you take, okay, and then connect like this. That is this is one transformer. And its secondary is here. And suppose I know the dots. Even if you do not know, then you have to do those two tests to find out either of these two tests conveniently. This is transformer 1, okay. This is one transformer, practical transformer, and you take the other transformer, which I have drawn here, its core, and here also suppose these two are dots. Okay. Now, the connection, suppose these are the HV side. HV side in this case 200 volt, 100 volt both are available in the lab, we will not bother. So, what you do? You connect these two transformer HV, in this case HV, it could be LV also, no problem, and connect them in parallel. And then here in this side you connect an ammeter and an wattmeter. Very interesting test. And apply rated voltage. That is, in this case for this transformer I will apply 200 volt 50 hertz, is not? That is what I will do. Suppose secondary I have not done anything, they are open. What do you think this ammeter will read and this wattmeter will read? If you apply this, these two transformers are manufactured by the same manufacturer of same ratings, they are expected to have same parameters, same core loss, this, that, etc. It is a very good assumption. Therefore, the current, the no load current will be drawn, this transformer will draw its no load current, only no load current, secondary are open, this transformer also will draw no load current. Therefore, I would expect this ammeter will read 2 times the no load current. That is, whatever ammeter reads, divide by 2 and tell that the no load current of each of the transformer is half of this. That is what. And what this wattmeter is going to read? Wattmeter with the secondary open for both the transformers, wattmeter will only record the core losses, sum of the core losses of these two transformers, because rated flux is there in both the transformer. Therefore, it will also read 2 times the core loss, is not, this wattmeter will read, and ammeter will read 2 times the no load current, and this wattmeter will read 2 times the core loss component of current. Now, as I told you, this, that is all. It is almost like an open circuit test, is not, secondaries are open. But now comes the interesting part. What is done now, and what will be, will there be induced voltage here? Yes, its value is 100 volt. Just I am putting this number so that things are very clear what I am talking about this way. Acha, suppose I join by a piece of wire these two terminals, and these two I bring it here. Here, these two terminals. If I connect a voltmeter across this, what will be the reading of the voltmeter? You think a bit and then tell, because polarities are this is plus, this is plus. So, they are opposing. So, it will be 0 voltage. So, between these two terminals, although this is connected by piece of wire etc., but voltage existing between these 2 points is 0. So, here voltage is 0. Now, what you do, you take an auto transformer here, I mean I should say variac, okay, in the laboratory. Oh, I should draw some space is necessary. So, you connect it like this. And here once again you connect an wattmeter and an ammeter, and make an arrangement so that you can apply small voltage here across this. If the pointer was at this point, no voltage you have applied and net EMF acting in this circuit is 0, nothing happens. Now, what you do with this primary energized, mind you, you apply little voltage, increase slowly. Okay? Then what will happen? This is the, what is the net EMF acting in the circuit now? This 100 volt will cancel out, they are as if not there. So, applied voltage divided by, so apply a little voltage, current will start flowing, is not? Current will flow. If current flows, suppose for some low applied voltage, suppose current, so increase this voltage such that rated current flows. What is the rated current of this side? It is 10, as I told you, given the transformer rating, immediately calculate rated currents, that is always important, 10,000 by 100, is not? 100 ampere is the rated current of the LV side. perhaps the test would have been better if we have energized 100 volt side current. Anyway, okay, 100 ampere. For understanding we are doing. So, I will apply such a voltage such that 100 ampere flows here. But the moment 100 ampere flows, suppose this way, 100 ampere is flowing this way. This is a secondary primary of a transformer having a magnetic core, and this is also primary secondary having its own separate magnetic core. But flux in the core cannot be changed, because KVL is to be satisfied here, that good old reasoning argument. Therefore, through the dot 100 ampere coming out for this transformer means that through this dot 50 ampere must flow. Through the dot current coming out, through the dot 50 ampere must flow. Now, similarly, for this transformer, it is just happening in opposite way. As I told you, if these two are dots, you can consider these two are dot as well and remove this. See, these are the things you must understand. So, through the dots here 100 ampere is coming out. Therefore, in this case through this dots 100 ampere must flow as so called, is it 50 ampere, sorry, that is correct. So, 50 ampere must flow. Is not? Therefore, I force some current to flow in this secondary coil. In this case LB side, I think it would have been better for this transformer even to consider 100 volt to be the rated supply, because ammeter rating and wattmeter, but anyway for just understanding purposes. So, this is 100 ampere and then reflected current here 50 ampere, 100 ampere reflected current this way. Apply KCL here, what will happen? 50 ampere comes in this direction, is not 50 ampere comes in and 50 ampere comes in here. So, this 50 ampere business never comes here. This current still remains 2 I naught, whatever is the no load current. Got the point? That is the most important thing. Now, this transformer windings are carrying rated currents. Therefore, rated copper loss will take place and rated flux is also present. So, rated core loss will also take place and also windings are carrying rated current. So, rated copper loss. So, both the losses are present here. This wattmeter draws supply from this supply, which is equal to 2 times the core loss of individual transformers. This wattmeter will record what? Only the copper loss 2 times the full load copper loss, is not? Because this current equivalent resistance, this that. From this source, second source here, which can supply large current, this ammeter reading of course will be not 2 times, these are in series. So, rated LV side current, this ammeter then should be based on this one 100 ampere. So, this is equal to rated LV current, in this case LV side current. So, apply such a small why small voltage will generate large current? It is because of the fact that net EMF acting in this circuit was 0, 100 volt which was caused by this application of 200 volt here, they always cancel out, and therefore, you can pump current now into this network. So, it will read P copper loss. Therefore, transformer will feel I am being used under full load condition, is not, because my windings are carrying rated current and my core is also carrying rated flux. So, both the losses are at their rated values. So, temperature rise, and if you do this test for a long time, say 1 hour, so that the thing attains a steady temperature. I mean telling just like that, put some thermometer there, I mean just telling that I can measure the temperature rise at some convenient places to say temperature rise here. What I am telling, that temperature rise must be higher compared to either for open circuit test whatever will be the temperature rise or short circuit test. Therefore, by estimating these copper losses, I will now be able to estimate the equivalent resistance I square this ammeter reading into R equivalent. From this I will be able to calculate new R equivalent, and from short circuit test whatever R equivalent I calculated, it will be higher than that. And from this variation of the resistance I should be able to predict what is the temperature rise. So, anyway, this is a very nice test for which you do not require 10 kVA load, it will only draw core loss and copper loss. So, and why it is called back to back test is also understood, you connect the secondaries in back to back manner, but the only condition is you must connect them in after noting down these dots correctly. For dots, do the previous test. You should not connect the secondaries just like that. This is dot, connect them, then 200 volt will appear. Is not, then your basic idea of carrying out the test will be lost. Anyway, I stop here today, but this circuit how it works, please think physically what is happening, then it will further, definitely it will enhance your understanding of transformer. Always remember, a transformer, 2 winding transformer, if secondary carries rated current, primary will also carry rated current. The direction of the current is decided by the dots. If through the dots rated current is coming out, through the secondary, through the dots current will come out. And these concepts I have used not only for 2 winding transformer, but also while analyzing the auto transformer. Okay. So, with this I stop here, I could not start 3 phase transformer, next time we will start. Thank you.